Welcome to today's problem walkthrough. We're diving into LeetCode number 771, titled Jewels and Stones. This is a classic string manipulation problem that challenges us to identify how many jewels are present in a given collection of stones. Stick around as we explore an intuitive brute force solution and discuss its nuances. Let's get started. In this problem, we are working with two strings, one called jewels and the other called stones. The jewel string represents the types of stones that are considered jewels, and each character in this string corresponds to a unique jewel type. On the other hand, the stone string represents all the stones you currently have, where each character corresponds to a specific type of stone. The goal is to determine how many of the stones you have are also jewels. Importantly, the problem specifies that the comparison is case-sensitive, meaning that lowercase and uppercase letters are treated as different types of stones. For example, a and a would be considered distinct. The input includes two strings, jewels with a length between 1 and 50, consisting of distinct characters, and stones with a length also between 1 and 50. The output will be a single integer, which represents the count of stones that are jewels. Now, let's look at some examples to understand this better. In the first example, the input jewel string is AA, and the stone string is AAAB. The output is 3. Here's why: the jewels are at and in the stone string, we see these jewels appear as a, and a. That gives us a total of 3 jewels in the stone string. In the second example, the input jewel string is Z, and the stone string is ZZ. The output is 0. In this case, the only jewel is Z, and the stone string contains 2 Z's, which do not match the jewel type because the comparison is case-sensitive. As a result, none of the stones are jewels, and the count is 0. Here's another example to further clarify. The jewel string is ABC, and the stone string is ACBAC. The output here is 6. This happens because the jewels are A, B, and C, and every stone in the stone string matches one of these jewel types. Specifically, the string ACBAC contains the jewels in the order A, C, B, A, C, and B, which gives us a total count of 6 jewels in the stone string. Finally, let's consider some important constraints and edge cases. The length of the jewel string will always be between 1 and 50, and all characters in it will be distinct. Similarly, the stone string will also have a length between 1 and 50. Both strings will consist only of English letters, with uppercase and lowercase letters treated as distinct. Now, for edge cases, if there are no jewels, though this isn't allowed by the constraints, the result would be 0. If none of the stones match any jewels, the result will also be 0. On the other hand, if every stone in stones matches a jewel in jewels, the result will be equal to the length of the stone string. These considerations ensure that the solution works for all scenarios while respecting the problem's constraints. To solve the jewels and stones problem, we considered 3 main approaches. The first approach is brute force. Here, the intuition is straightforward. For each stone in the stone string, we compare it with every jewel in the jewel string. If a match is found, we increment the count. While this method is easy to implement, it involves a nested loop, which results in a time complexity of O, n asterisk m, where n is the length of stones and m is the length of jewels. It uses no extra space, so the space complexity is O, 1. However, the major drawback is its inefficiency for large inputs, as the nested structure makes it computationally expensive. Now, the second approach uses a hash set to optimize the process. Instead of repeatedly comparing against the jewel string, we first convert it into a hash set. This allows us to check if a stone is a jewel in constant time, O, 1. The time complexity becomes O, n plus m, where m accounts for the conversion of jewels into a hash set, and n accounts for iterating through stones. The space complexity is O, m, because of the hash set storage. This approach is significantly faster and better suited for larger inputs as it avoids nested loops. Lastly, we briefly considered a dictionary-based approach. Here, the idea is to count the frequency of each stone type using a dictionary and then sum up the counts of the stones that are jewels. However, this solution introduces unnecessary complexity, as the exact frequency of non-jewel stones is irrelevant to the problem. The dictionary-based approach, while efficient in terms of time complexity at O, n plus m, has a higher space complexity of O, n plus m, as it stores frequencies for all characters. This additional memory usage and complexity make it less ideal for this specific task. With these considerations in mind, the hash set approach was chosen as the optimal strategy. It offers the best balance between simplicity and efficiency, with a time complexity of O n plus m and minimal space requirements, as it only uses a hash set to store the jewels. The key insight here is that checking membership in a hash set is much faster than iterating through a string, which eliminates the inefficiencies present in the brute force method. When comparing the three approaches, brute force is the simplest but least efficient, especially for larger inputs. The dictionary approach shares the same time complexity as the hash set method but introduces unnecessary memory usage and complexity. The hash set method, on the other hand, is both fast and lightweight, making it the most practical solution. This strategy focuses on clarity, speed, and scalability, ensuring it handles large inputs effectively without overcomplicating the implementation. To solve this problem, we are tasked with determining how many stones in the string stones are jewels, as defined by the string jewels. Each character in jewels represents a unique type of jewel, and each character in stones represents a stone we have. Our goal is to count how many of these stones are jewels. One approach to solving this is the brute force method, which systematically compares each stone with every jewel to find matches. First, we validate the input by ensuring that both jewels and stones are non-empty strings. If either of them is empty, the result is 0 since there are no jewels or stones to compare. Next, we initialize a counter variable called count, starting at 0. This variable will track the total number of stones that are also jewels as we proceed through the algorithm. Once the input is validated and the counter is initialized, the algorithm begins by iterating through each character in the stone string, treating each character as an individual stone. For every stone, we then perform an inner iteration through the jewel string. This inner loop allows us to compare the current stone with each jewel type, one by one. If the current stone matches a jewel, we increment the count variable by 1. This ensures that every match is accounted for. Finally, after all comparisons are completed, the algorithm returns the value of count, which represents the total number of jewels found in the stones. While this approach is straightforward, it involves comparing every stone with every jewel, leading to a nested loop structure. The brute force approach works because it exhaustively compares every stone with every jewel, ensuring that no potential matches are missed. However, this method is not efficient. The time complexity of this approach is O n *m, where n is the length of the stone string and m is the length of the jewel string. This is due to the nested loop structure, where each stone is compared against every jewel. The space complexity, on the other hand, is O(1), as we do not use any additional data structures beyond the counter variable. It's also important to consider edge cases. If the jewel string is empty, there are no jewels to compare against, so the result is 0. Similarly, if the stone string is empty, there are no stones to check, resulting in 0 as well. Interestingly, if there are duplicate characters in the jewel string, it doesn't affect the result because our algorithm counts matches based on characters individually, not their frequency. In this approach, we rely on two main data structures, the counter variable count and the input strings jewels and stones. The count variable is a simple integer that tracks the number of matching stones, and the strings are directly used for comparison without requiring any additional memory. While this method is easy to implement and guarantees correctness, it is inefficient due to the nested loop structure. A more optimized solution involves using a hash set to store the characters in jewels. By doing so, we can reduce the time complexity to O n plus m, as set lookups are O(1). In this optimized approach, we iterate through the stone string and check whether each stone exists in the hash set. This significantly reduces the number of comparisons. For now, the brute force method provides a clear and simple foundation for understanding the problem and its solution, setting the stage for exploring more advanced techniques in the future. This implementation solves LeetCode problem number 771 jewels and stones efficiently. The goal is to count how many stones are jewels. First, we convert the jewel string into a set, stored in jewel_set. Using a set ensures constant time lookup, which is faster than checking membership in a list. This is especially beneficial when the number of stones is large. Next, we initialize a count variable to 0. This will keep track of how many stones are jewels. We then iterate over each character in the stone string. For each stone, we check if it exists in the joule_set. If it does, we increment the count by 1. Finally, the function returns the count, which represents the total number of stones that are joules. This solution is efficient, with a time complexity of O, n plus m, where n is the number of stones and m is the number of joules. The space complexity is O, m, due to the storage of the joule_set. This approach handles all edge cases, such as when there are no joules, no stones, or duplicate joules. This is the Java implementation of LeetCode problem number 771, Joules and Stones. The logic mirrors the Python implementation, where we use a hash set for efficient lookups of joule types. The method numberJoulesInStones iterates through the stones and counts how many belong to the set of joules. Key differences include explicit type declarations and the use of Java's hash set for managing joule types. In this example, we are given joules equals AA and stones equals AAAB. To solve the problem, the first step is to convert the joules string into a set. This gives us joule_set equals a. Using a set here is important because it allows us to check whether a stone is a joule in constant time, which makes our solution efficient. Next, we initialize a counter count to 0. This variable will help us keep track of how many joules we find as we go through the stone string. Now, as we iterate over the stones, we check each character to see if it exists in joule_set. The first stone, is in the set, so we increment count to 1. The second and third stones are both and since it is also in the set, we increment count to 2, and then to 3. The remaining stones, B, are not in the set, so the counter stays at 3. Finally, the function returns the value of count, which is 3. This tells us there are 3 joules in the stone string. Here, we have joules equals Z and stones equals AAAB. As usual, we start by converting the joules string into a set, resulting in joule_set equals Z. Then, we initialize the count variable to 0. This time, as we iterate over the stone string, we notice that none of the stones B, 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 and B are in the joule_set. Because of this, the count remains 0 throughout the iteration. Once we've checked all the stones, the function returns the value of count, which is 0. This means there are no joules in the given stone string. In this final example, we are given joules equals ABC and stones equals ABCAP. After converting the joules string into a set, we have joule_set equals B, C. With our count variable initialized to 0, we begin iterating through the stones. The first stone, is in the set, so we increment count to 1. The second stone, B, is also in the set, so count becomes 2. The third stone, C, is in the set as well, bringing the count to 3. This pattern repeats for the second half of the stone string. B and C are all joules, so the count increases to 4, 5, and finally 6. At the end of the iteration, the function returns count, which is 6. This indicates that all 6 stones in the string are joules. In this solution for the joules and stones problem, the time complexity is determined by 2 main steps. First, we build the joule_set from the joules string. Since creating a set involves iterating over all the characters in the string, and each insertion into the set has an average time complexity of O(1), this step totals to O(m), where m represents the length of the joule string. Next, we iterate through the stone string to check if each character exists in the joule_set. Membership checks in a set are efficient, averaging O(1) per lookup. With n being the length of the stone string, this loop contributes O(n) to the overall complexity. When these steps are combined, the total time complexity of the solution becomes O(m plus n), as the operations are performed independently of one another. The space complexity of this solution is primarily driven by the storage requirements of the joule_set. This set contains all unique characters from the joule string, so in the worst case, if all characters in joules are unique, the space required is proportional to the length of the string, or O(m). Beyond this, the solution uses only a constant amount of extra space for variables like count and the loop iterator, which means they add O(1) to the overall space complexity. As a result, the total space complexity is O(m), driven by the need to store the set of unique joules. When we analyze the solution across different input scenarios, the time complexity adjusts accordingly. In the best case, if stones is empty, the loop does not execute, and the time complexity is simply O(m) for building the joule_set. Conversely, if joules is empty, the set construction is skipped, and the complexity reduces to O(n) for iterating over stones. On average, for typical non-empty inputs, the time complexity remains O(m plus n) due to its linear dependence on the size of both inputs. In the worst case, where both joules and stones are non-empty, the complexity stays O(m plus n). For comparison, a brute force approach, which checks each stone against every joule, would require a nested loop and result in O(m*n) time complexity, making it significantly less efficient than our optimized solution. The optimized approach leverages the properties of a set to drastically reduce the time complexity compared to a naive solution. By storing the joules in a set, membership checks for each stone become O(1) on average, transforming the overall time complexity to O(m plus n), which is much faster than the O(m*n) complexity of the brute force method. While the use of a set does introduce an additional space requirement of O(m), this trade-off is justified by the significant time savings achieved. Mathematically, the solution processes each character in joules and stones in separate loops, ensuring their complexities add linearly. With set operations like insertion and membership check averaging O(1), the solution achieves an optimal complexity of O(m plus n), which aligns well with the problem constraints and ensures efficiency for large input sizes. When working on this problem, there are some common mistakes to watch out for. First, not accounting for edge cases can lead to runtime errors or incorrect results. For instance, if the joule string is empty, no stones can match as joules, so the output should be 0. These edge cases can easily be overlooked if you're not testing thoroughly. Another common issue is using inefficient nested loops to check each stone against every joule. This brute force method can quickly become impractical for large inputs, as its time complexity is O(n*m). Next, pay close attention to case sensitivity. If the problem doesn't specify, you need to handle uppercase and lowercase characters distinctly. For example, if joules contains AA, both lowercase a and uppercase a need to be treated as separate joules. Additionally, using the wrong data structure, like a list instead of a set, can significantly impact performance since lists have O(n) lookup time, while sets provide O(1) on average. Finally, avoid unnecessary operations like repeatedly converting joules into a set inside a loop. Instead, compute the set once to save time and reduce overhead. A key insight for this problem is the importance of efficient membership testing. Using a hash-based data structure, such as a set, drastically improves lookup time and is central to optimizing your solution. This approach aligns with a broader pattern seen in similar problems. When tasks involve membership testing, filtering, or counting, hash maps and sets are incredibly effective. To demonstrate your problem-solving skills during an interview, start with a brute force solution and explain how you'd iterate toward a more efficient approach. This thought process helps interviewers understand your ability to optimize under constraints. You may also encounter variations of this problem, such as performing case-insensitive comparisons, handling non-alphabetic characters, or modifying the solution to return the actual joules found rather than just their count. If you're preparing for interviews, consider related problems like LeetCode 1365, which involves comparisons in membership testing, or LeetCode 242, which uses hash maps for counting frequencies. Problems like LeetCode 387 and LeetCode 202 further demonstrate the versatility of hash-based approaches in handling unique characters or detecting cycles. There are several approaches to solving this problem, each with its trade-offs. The brute force method uses nested loops with a time complexity of O(n*m), where n is the length of stones and m is the length of joules. While this approach is straightforward and suitable for small input sizes or quick prototypes, it's not feasible for larger inputs due to its inefficiency. A more optimal solution involves using a set for joules, allowing for O(1) average lookup time. This approach has a time complexity of O(n plus m), and is ideal for most cases, though it requires additional memory to store the set. If the problem constraints limit the input to a fixed set of characters, such as only lowercase or uppercase letters, bitmask optimization is another option. By representing characters as bits, this method reduces complexity to O(n) and eliminates the need for sets. However, it's only applicable in scenarios with small, fixed character sets. Each approach has its strengths and weaknesses, so understanding the input constraints and requirements is key to selecting the best solution. Great work! In summary, we tackled the jewels and stones problem using a brute force approach. This solution introduced key concepts in string manipulation and complexity analysis. Remember, this problem is an excellent stepping stone for more advanced challenges. Thank you for watching, and be sure to subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!